Welcome to the Deep Dive, the place where we give you the essential structural analysis toolkit, but in just minutes.
Right.
Today, we're diving deep into the core methods that analytical chemists use. We're talking about a combination of separation and spectroscopy.
The tools they use to figure out what a molecule actually looks like.
Exactly. To verify, quantify, and ultimately discover the full structure of organic molecules.
It really is the ultimate chemistry detective kit. So our mission for you today is to give you a rapid, crystal clear understanding of the key concepts, the calculations, and the rules for chromatography and nuclear magnetic resonance spectroscopy,
Or NMR.
NMR.
hmm
And it's important to remember these techniques aren't solo acts. They work together, with things like mass spec and IR spectroscopy to give chemists the complete molecular fingerprint.
And before we get bogged down in chemical shifts and all that, let's just quickly establish why this matters outside of a chemistry lab. I mean, why are we talking about the structure of simple molecules?
Well, because the physics we're about to discuss scales up
How?
a lot. If we connect this to the bigger picture, the same underlying principles are used all the time in biology to map out the structures of massive molecules, especially proteins.
Oh,
Using really sophisticated NMR data, scientists can figure out the precise distance between thousands of atoms, and that reveals the overall 3D shape, which we often see visualized as those famous um, ribbon diagrams.
right. The ones developed by Jane Richardson back in the 80s.
The very same.
Ah,
And understanding these structures, often in solution, is absolutely fundamental to modern medical research.
that's powerful context. Okay, let's start with the first step in any analysis, which is separating the components of a mixture. We are talking about chromatography.
At its heart, chromatography is fundamentally a race.
A race.
A race to separate a mixture based on how much the components like to stick to one thing versus another. And you always have two essential players here, the mobile phase and the stationary phase.
Okay, so think of it this way. The mobile phase is the vehicle, right? The liquid solvent or gas that's actually moving the mixture along.
Exactly. And the stationary phase is the track. It's the material that stays put, whether that's specialized paper, solid powder on a plate, or liquid trapped in a column.
And the whole mechanism relies on what you call differential affinity.
Right. Components have different partition coefficients, which is just a fancy way of saying they have different preferences, different solubilities between the mobile and stationary phases.
So a component that loves the mobile phase just rushes on through.
Rushes through quickly, yeah. While a component that prefers sticking to the stationary phase gets held back, it moves much more slowly.
Okay, so when we talk about paper chromatography or thin layer chromatography, we quantify this race using the RF value, the retardation factor. How do we calculate that?
It's a simple ratio. You calculate RF by taking the distance moved by the solute, and that's from the center of the component spot, and you divide it by the total distance the solvent front has moved.
And crucially, the RF value is always between 0 and 1.
Always. But you should know that these values are, well, they're meaningless unless you compare them under absolutely identical conditions. Same temperature, same solvent, everything has to be the same.
Let's pivot from paper to TLC then. Thin layer chromatography. The setup looks pretty similar, but the mechanism for separation changes a bit, doesn't it?
It does. In TLC, the stationary phase is usually a solid, commonly silica or alumina, spread very thinly onto a glass slide. And because it's a solid, the dominant mechanism shifts from partition to adsorption.
So it's sticking to the surface.
Exactly, adsorption onto the surface. And the rule is simple. Polar molecules have a greater attraction for that polar solid stationary phase. So they're adsorbed more strongly and consequently they travel more slowly up the layer.
And I imagine TLC is often preferred in the lab because it's faster,
Yeah.
right? And it uses incredibly small samples.
Which is vital in forensic applications. We're talking about identifying microgram traces of a drug or maybe an explosive residue.
Makes sense. Okay, so now let's go from running a race on a flat track to, I don't know, running it through a massive obstacle course. Gas liquid chromatography or GLC.
Right, and the first rule here is that your sample has to be volatile. It has to be easily vaporized into a gas.
So we inject the volatile sample. Can you describe the conceptual structure of the column for us?
Sure. The stationary phase is a long, narrow column packed with a solid support that's coated with a non-volatile liquid. Think of a high boiling point, non-polar hydrocarbon.
And the mobile phase isn't a liquid this time?
No, here it's an inert carrier gas, something like helium or nitrogen, which just sweeps the vaporized sample through the column.
So the separation is still partitioned then. It's just between the gas mobile phase and the stationary liquid phase. What happens to the components?
Well, nonpolar components will be more soluble in, and so they'll interact more strongly with that nonpolar stationary liquid.
So they get held up?
They get held up longer, and they exit the column more slowly than components whose molecules are less polar,
And the key result, the measurement we care about in GLC, is the retention time.
which is simply the amount of time it takes each component to travel from the point of injection all the way through the column to the detector.
So retention time is like a fingerprint.
It is, but with a major caveat. Similar compounds can have very, very similar retention times. This means that to use it for identification, you have to control every single experimental variable temperature, flow rate, column type with extreme precision, and then compare it to a really robust database.
That structural ID is crucial, but GLC is also fantastic for quantitative analysis. How do we figure out the percentage composition of a mixture from the graph it produces?
The fundamental concept here is that the area under a component's peak on the chromatogram is directly proportional to its concentration.
Assuming the detector responds equally to everything.
Exactly, assuming that. So to find the percentage of, say, component A, you just take the area of peak A, divided by the sum of the areas under all the peaks in the spectrum, and multiply by 100.
It's a beautifully simple ratio once you have the data. And this kind of high-level analysis is what lets chemists do critical checks, like verifying fuel composition in high-performance motors.
Or ensuring quality control in industrial processes, yeah.
Yeah.
And that leads us perfectly into the next analytical powerhouse, nuclear magnetic resonance, NMR.
Right. So while chromatography tells us what is present and how much, NMR tells us how all the atoms are actually connected to each other.
Now, the physics gets really fascinating. The basic mechanism hinges on the fact that the nuclei of hydrogen atoms, so protons, have this intrinsic property called spin.
Which causes them to act like tiny microscopic bar magnets.
Precisely. So when you put a sample with these hydrogen nuclei into a powerful external magnetic field, they align either with the field, which is a lower energy state, or against it, which is a higher energy state.
And then you hit them with radio waves.
You blast the sample with radio waves. And when the frequency of those radio waves matches the tiny energy difference between those two states, the nuclei absorb that energy and flip their alignment. And we detect that absorption.
And the critical structural insight comes from the fact that the energy needed to make a proton flip, what we call the chemical shift, is different depending on its molecular environment.
Exactly. The electrons buzzing around the proton actually shield it a little bit from the external magnetic field. So protons in different chemical environments, say a CH3 versus a CH2 next to an oxygen, they experience different levels of shielding, so they absorb at slightly different frequencies.
And we measure all these shifts relative to a 0 point, don't we?
We do, yes. Our standard reference compound is tetramethylsilane, or TMS.
Why that one?
Well, it's inert, it's volatile, and all 12 of its hydrogen atoms are identical, so it gives us one single sharp reference peak that we just define as 0 parts per million chemical shift.
And a quick but really crucial practical detail, why do we need special solvents like CDCl3 deuterated chloroform?
Because we're only interested in detecting the hydrogen-1 protons in our sample.
Ah, so regular chloroform would get in the way.
It would interfere dramatically. Its own protons would show up. Deuterium, or hydrogen-2, doesn't absorb energy in the same range, so using a deuterated solvent means only our sample's protons appear on the spectrum.
Okay, let's start interpreting the results with low-resolution NMR. If we look at ethanol, CH3, CH2OH, we see 3 peaks. What information are we getting immediately?
Low-res NMR tells you 2 things. First, the number of peaks equals the number of non-equivalent proton environments. So for ethanol, that's 1 for the OH, 1 for the CH2, and 1 for the CH3.
3 environments, 3 peaks.
And second, and this is crucial, the area under each peak is directly proportional to the relative number of equivalent protons. So the peak for the CH3 group will have 3 times the area of the OH peak.
So low resolution gives us the proton ratios, and if we use chemical shift tables, the type of group. But to truly confirm how they're connected, we need high-resolution NMR. We need to see the splitting patterns.
That's where this structure just snaps into place. In high-res spectra, we see that what looked like a single peak is actually a cluster of smaller peaks. This is called spin-spin coupling.
And it's caused by the tiny magnetic fields of neighboring protons interfering with each other.
They're influencing the absorption of the proton we're looking at. And this interference is governed by one of the most important rules in structural chemistry, the N+1 rule.
The N+1 rule.
Absolutely. The N+1 rule states that the number of signals a peak splits into is N+1, where N is the number of hydrogen atoms on the adjacent carbon atom or atoms.
Okay, let's stick with ethanol. The CH2 protons are next to the CH3 group, so N equals 3.
Right, so 3 plus 1 equals 4. That CH2 peak splits into a quartet, 4 peaks.
And conversely, the CH3 protons are adjacent to the CH2 group where N equals 2.
Correct, so 2 plus 1 equals 3. That peak splits into a triplet. The splitting pattern confirms who the neighbors are, which tells you the connectivity.
Now, there's a really vital exception here for OH and NH protons. Why do they usually show up as unsplit singlets, even when they have neighbors?
This is due to rapid proton exchange. The OH proton it's labile. It rapidly jumps back and forth with other OH molecules or even traces of water in the sample.
So it's moving too fast.
It's moving so fast that when the adjacent CH2 group looks at it, it just sees an average, blurry, non-spinning signal over time. So the signal isn't split.
So if you suspect you have an OH or an NH group, how do you confirm it definitively with the spectrum?
You use the deuterium exchange test. You add a small amount of deuterium oxide, D2O, to your sample.
Heavy water.
Heavy water. The deuterium atom exchanges with that labile proton. And since deuterium doesn't absorb in the proton NMR region, the peak for that OH or NH group simply disappears from the spectrum. That disappearance is your confirmation.
Let's quickly synthesize all this using the example of ethyl ethanoate.
Okay, so you see 3 distinct peaks with relative areas of 3, 3, and 2. The splitting is what confirms the structure. The peak with an area of 2 is a quartet, meaning it has 3 neighbors. It must be the OCH2 part next to a CH3.
Okay.
And one of the 3 proton peaks is a singlet, meaning it has 0 neighbors. That tells you it's attached to a carbon that has no hydrogens on it, which has to be the carbonyl carbon of the ester, the H3CC double bond O part.
And you put those fragments together and you get the full structure.
That's the magic of NMR.
It really is.
Uh-huh.
Okay, finally, let's briefly compare all this to carbon-13 NMR spectroscopy. Now we're analyzing a tiny fraction of the molecule, right?
A very tiny fraction.
Yeah.
We can only detect the carbon-13 isotope, which is only about 1% of naturally occurring carbon. Carbon-12 is invisible to NMR.
So what simplifies the interpretation compared to proton NMR?
Well, the interpretation is significantly easier because the spectrum just produces one discrete vertical line for each non-equivalent carbon-13 atom.
So no splitting.
No complicating spin-spin coupling. There is no N+1 rule for you to worry about here at all.
And the other major difference?
The height of the line is not proportional to the number of equivalent carbons. You cannot use the height to determine how many carbons are in that group.
Okay, good to know.
Also, remember to ignore the small signal that often appears near 80 parts per million. That's just the carbon-13 from the deuterated solvent, the CDCl3.
So for something symmetrical like propanone, which has 3 carbon atoms, the 2 methyl groups are equivalent, so we only see 2 peaks.
Exactly. One for the 2 equivalent methyl carbons and one for the carbonyl carbon.
And for more complex molecules like ethylbenzene, even the ring carbons, though they're similar, they're slightly affected by that attached ethyl group.
Which gives you a whole cluster of distinct lines in the aromatic region of the spectrum.
That summarizes our intensive deep dive into these tools. So to recap the major takeaways for you listening, chromatography separates components based on differential affinity. It's a race, and we quantify it with RF or retention time.
And NMR probes the specific chemical environment using chemical shifts. It gives you crucial connectivity details from the peak area and, of course, that powerful N+1 splitting rule, allowing us to literally build the molecular structure piece by piece.
The ultimate lesson here really is that no single technique gives you the whole answer.
No, it's the combined power of separation, quantification, and all this spectral analysis that gives a chemist the full, verifiable picture of any unknown organic compound.
And here is a final thought for you to carry forward. Think back to those ribbon diagrams of proteins we mentioned at the very start. It is the exact same core physics, the tiny magnets, the chemical shifts, the magnetic resonance that allows us to understand those incredibly large and complex protein structures in solution. And that's what's driving breakthroughs in everything from drug discovery to vaccine development.
Thank you for joining us on this deep dive into analytical chemistry. We hope you feel thoroughly informed and ready to tackle your next spectrum.